So now some more serious stuff on optimization that we're going to see in the next lecture. So in the next lecture, perhaps we can cover up to this point. I'm not 100% sure if we can cover stochastic gradient anyway. But then in lecture 3, we're going to spend more time on variation of this stochastic gradient and with memory. But what are they? In general, we can say convex optimization is, with unconstrained format, is when f and w, both of them are convex. Then minimizing f over that convex set is unconstrained convex optimization. And this is the common form that you will see in machine learning, and in particular machine learning over network as well. We can have some constraints, but then the way that we will handle those constraints is using Lagrangian multiplier and then putting them in the objective function somehow, and then ending up to a lower bound on the optimal solution of the original problem. But why convex? Because we can have a very good guarantee on that some local optimal is global optimum there in this regime. Doesn't mean that these problems are easy to solve, but then definitely easier than other classes of the problems, optimization problems. We can have linear convergence rate. Essentially, it means that at every iteration, the solution that the algorithm will output is decreasing. Well, it's moving toward the optimal solution, but by a linear rate. So this is one thing that we can say. So after t iterations, the distance to the optimal solution could be something to power t, for instance. So that's a very good. But so this is called linear convergence rate. We will see that formally later in the next lecture. And then we can have some very, very strong theories of duality to check the convergence, to see if we are happy with the current solution or not by checking the lower bound of the solution and then see if the lower bound is close to the solution of the algorithm at this step or not. If not, then we should do something more. OK. Now, another thing is that we do have some very efficient solvers for most of convex optimization problems. And then if we do have a strong convexity and a smoothness, well, to have linear convergence, we need to have a strong convexity and a smoothness. We will see those definitions later on in the next section, in the next lecture. But we can have some efficient solvers. It doesn't mean that we cannot apply those solvers on non-convex problems or problems with non-smooth problems or non-strongly convex objective functions. We can definitely apply them. And in particular, this one will work well, not magic, but then this works somehow magically in most of situations. But we will try to somehow explain why it works. But this is the idea. So we do have some efficient solvers that they were originally developed, most of them, not all, originally developed for convex optimization. We can analyze them theoretically in the convex region. But then we can apply them on non-convex as well. But then we can get insight from the easiest class of problems, which is convex. Some of them, let's say f is a finite sum. So here, for instance, this 1 over n summation of f of xi parameterized by w. Just say that this f of xi parameterized by w is the quadratic loss term, for instance. Of the prediction, and we have the total loss, which is the average of those on the individual samples in the training. Okay, so something like that, a finite sum. The gradient descent, which is one of the most popular algorithm, we will see the convergence of this very simple algorithm. But what it does is that it say at every iteration wk plus 1. So wk plus 1 is the output of the algorithm at iteration k plus 1. Is the previous wk minus alpha k some positive step size or learning rate, we can call it as well. Positive step size and gradient of f. Well, this is true for differentiable functions. If it's not differentiable, we can just replace this gradient with subgradient of the function anyway. But the simpler case is if it is differentiable, then the gradient of f evaluated at the previous point. So very simple algorithm can work very efficiently. So this is a local information, this gradient, because you're going to perturb the function a little bit around wk to find this gradient. locally around that point, but then that's just enough to make sure that you can converge over convex optimization landscape. Then, to improve that, well, this seems very nice, very simple, but just to give you some perspective, it's not actually very simple. Well, the performance can be actually horrible anyway. But just to give you an example, just imagine that the surface of the convex optimization is something like that. So these are like sub-level sets of the convex optimization if the optimization function is like norm 2, for instance. So this is the norm 2 function, and these are the sub-level sets of that norm 2 functions. And then you're going to start from some point here in the function. So this corresponds to something like that, OK? And you're going to start from some point here. But then here, the optimization landscape is pretty good, actually. Something called condition number, you will see that later in the next section. But something called condition number is really good here. Then at every iteration, you're going to move toward this. So this is the actual gradient. And then you're going to move toward the negative of the gradients. And then very fast, you can converge to the optimal solution here. But then what happens is that in most situations, we don't have this. So what we do have instead is something like that. Oh, it's not working. Good. So let me use this. So you're going to have something like that. Then what happens is that you're going to start, for instance, from this point. Then you can move towards some point here. Then you can have a lot of oscillations until you find the optimal solution. And then the number of these oscillations could be quite high, depending on the condition number of the problem. So in that case, if you just run the gradient descent algorithms, you can converge, but not in a feasible time. So if you want to have a real-time solution, for instance, then definitely gradient descent is not the way to go. This is the first thing about the iteration complexity. But on top of that, you can have some even more serious problems. So just imagine that this setup. So let me use this one now. Just imagine that WK belongs to R 2 million. OK, so you have 2 million parameters, and then you want to optimize over 2 billion parameters, and then you want to optimize over these 2 billion parameters, for instance. OK, we'll make it even simpler. So 2 million parameters doesn't matter anyway. And so this is a quite long vector, and then you want to optimize over that. And just imagine that n is, let's say, I don't know, 100. Some very simple examples, OK? And just imagine that this n is not the size of the data set, but instead n is a number of sub-data sets. So you have hundreds smaller data sets that are somehow distributed across many different nodes. So every node has just one of those small data sets. And then what it happens is that there is a master node. We will see that later on in lecture 4 or 5. Well, 5, I guess. So what happens is that there is a master node that asks individual nodes to compute the gradients. So they will compute this term, this individual summand here. So this gradient is actually, you can write it down as 1 over n summation of the gradients with respect to those xi's. So they will find their own gradient with respect to their own data set, and then they will send it to some master node. And the master node will run this gradient descent. So collect all the smaller gradients, subterms here, find the gradient, and then run one iteration of gradient descent. So first of all, we may need a lot of those iterations. So this is aside. Every iteration needs sending a vector of 2 million parameters. And it could be just quite high, because you can imagine that individual value here can be a floating point, so 32 bits per value. So it's quite high. And then we can have a lot of those numbers. So it can go wrong in many different ways of the communication here. So some of them may not be able to send their data, so they need to repeat and repeat and repeat if there are some lossy communication channel in that scenario. Even if there is no loss in the communication, still they need to communicate this. OK? And what happens if n now is 10 to the power 9? Just giving another extreme example. Then even computing the gradients is really high. Why? Because you need to find 1 million of these guys and then find this average over that million. OK. So just give you some insights of what you will see later on in the lecture. Steepest descent is the first attempt to address the first problem of the iterations complexity, try to reduce the number of iterations a little bit by updating instead of toward the negative of the gradient toward some other directions. So let's call g of w a descent direction. You will see the definition, but essentially it should remain on the same half space of the gradient. So it's like a positive semi-definite form of, well, multiplication of PST matrix and the gradient. So it should be in the same half space. But then you will somehow move toward the negative of that. So if I want to give you an example here, for instance, it says that the gradient here is this. So steepest descent will move toward the negative of the gradient, but it's gradient descent. But the steepest descent can move toward this direction. So it can move here, and then from now on, it can move toward, well, in the ideal case. This is what's happening in Newton method, for instance. OK? Then, in order to address other problems, like this problem with n, especially, then we need algorithms in the class of Robin-Monroe's algorithm, so stochastic gradient descent, which have been there for quite a long time, but recently they're being used a lot. Especially, we will see in the next slide that if we have a non-convex optimization, then this might work much better than this in some scenarios. So essentially what it does is that it says that wk plus 1 is wk minus alpha k. The gradient, it could be some form of descent direction as well. But then the gradient evaluated at wk and one specifically randomly selected sample. It could be mini batch, so you can have approx. So essentially what this form, this guy here, this gradient of x is, or wk, is an approximation of the actual gradient, called also full gradient. GW is a descent direction. So just give you an example. Let's say here is the gradient. So this is the half space, OK? And this is the gradient of f of wk, OK? So G, in general, can be any vector here, as long as it's in the same half space of this guy. So what in the gradient descent, we are using minus of this, and then we are moving toward that direction. But we have seen that moving toward the minus of that in this scenario could be very problematic, right? Because we're going to need a lot of these isolations to converge. But then what this guy tries, so this descent direction says that, OK, let's change that direction. And then instead of moving toward this, so the negative of the gradient, let's move toward the negative of some descent direction. So something like that. It helps to somehow precondition, in general, this guy. So if you multiply that positive semi-definite matrix, so the way, let's say, if you somehow multiply the way that you generate this descent direction with the optimization landscape, essentially it tries to make this guy a little bit more similar to that, and then run the gradient descent on somehow this. So precondition function. We will see next lecture. Here is just an overview. So the question was how we will find this descent direction. We'll see that in the next lecture. But then that's the whole idea. So any direction that remains in the same half space is fine. Okay, it can work in theory, but then which of them are the optimal one? We will see that. In some very simple scenarios, we can find the optimal directions. Okay. Stochastic gradient descent is, we replace, let me keep it down. We replace the computationally heavy gradient, which could be very heavy computationally, with some locally, perhaps, it doesn't have to be locally anyway, but usually with some local approximation of that gradient. And magically, it can work actually a lot. Very, very good actually in some scenarios. So you can imagine that this gradient here is an approximation of the true gradient. So essentially, this is the the true gradient plus some noise, okay? And then we will see the role of that noise in the next slide. It can play a really good role. So in this scenario, we don't have any memory. You will have a data set. You will find the gradient with respect to one sample in the data set. But then we can add some memory to record something. We will see the impact of this. But then we can end up to some things much newer. So this is from 1950 or something in that order. But then here we can actually move towards something recently after 2010 or so. With, for instance, SVRG, stochastic variance reduction gradients, or stochastic average gradient, SAG, or some extensions of that, where we can improve a lot the convergence, both in terms of the number of iterations and the computational complexity. And then we can have some acceleration methods where we're gonna wait. We don't go in this form of iterations. We don't go always toward the negative of the gradients. So we have a convex combination of our previous solution plus negative of the gradient. So if you again look at this, it says that you can see that in most cases, we need to move toward this direction much more than this direction. So it says that, OK, let's put much more weight as we move on. So here you can see as we move on, we put more weights on the previous solutions as well. OK? So the terms that remains in the previous solutions will somehow push the whole things to move toward this guy. OK? So it can help a little bit, again, the optimization landscape. Improve that. We will see that in the next slide, next lecture. So these are the sort of things that you will see in lecture 2 and 3. But then it's not the end of the story, because we will see these guys especially all over again in all the lectures. OK, then what happens in machine learning is that, especially in supervised learning with deep neural network, optimization landscape is non-convex mostly. So this is a very simple form of non-convex objective function, y2 minus x2. And among all other problems, well, first of all, local optimality doesn't mean global optimality. So for instance, consider this function. So local optimality is like this guy, or even this guy. Doesn't mean global optimality at all. And local information may not be enough, especially first-order local information, which was enough for convex optimization to say that this is globally optimal. It may not be enough here to say that this is globally optimal. But what can happen here also is something called saddle point, which is something like that. So it's like minimum in some directions and maximum in some other directions. So if you go with first-order condition, like the gradient is smaller than something, to say that, OK, if we go with, so at the end of the day, this is neither maximum nor minimum, right? But then first order optimality condition says, actually, this point can pass the first order optimality condition, and then the algorithm can stop by observing some points like this, right? And this is problematic because this is neither minimum nor maximum. So what we can do is that now here, magically, a stochastic gradient helps here. Because in a stochastic gradient, we do have some noise, right? So just magically, so here we move toward the negative of the direction. And if you run gradient descent, definitely we will stop at this point, OK? But then here, let's say that this is not a saddle point. So something like this, where we do have a saddle point here. I can make it even a smaller saddle points. So something like that. So the gradient descent will stop here because the value of the gradients are so small here. Of course, you can run it and run it and run it. Ultimately, it can go to the downhill, but then definitely your algorithm will stop at some point here due to the first order optimality criteria. Then a stochastic gradient noise, it somehow, at some point, let's say that the gradient is here. The gradient value is very small. But then the noise of that may somehow jump this sample instead of the next sample. Instead of being here, it may be able to jump the next sample somewhere here. OK? This is just due to noise in the gradient. It might put the sample right here as well, right? But then there is a chance that it can work like that. So in this case, there is a chance that the sample can move downhill, and it may not stuck in that saddle point. We will see that. and how we can efficiently use that artificial noise that can be either generated during the stochastic gradient, or we can just add that manually to escape this saddle point, and then we can see how we can efficiently do that. This is called perturbed gradient descent. Essentially, we have this gradient descent, and whenever the first order optimality condition satisfies, then we're going to perturb intentionally the gradient to see if we're going to converge again to the same solution or not. So very simple algorithm, but it can work. Okay. And last but not least, the application areas. So it doesn't mean that this is just, we are not limited to these applications. In the next set of slides, you will see some applications. And I have said more or less about them. But then these are sort of things that we will see. So let's say that we have a graph of some vertices and some edges, and then graph can be something like that, a multi-agent system, for instance, in the general setup. If some examples are like in computer networks, those new eyes, so the vectors, the vertices can be workers, and the edges could be a communication link. So it could very well, in the next slide, we will see a realization of this guy. In wireless networks, for instance, those nodes could be links, and well, link, a communication link, I mean. And an edge could be an interference from some node to one link to another link to say how we can allocate the resources with minimum interference, for instance. And then in biological networks, for instance, it could be like a sensor. Every vertex and every edge could be, again, a communication link. And the whole idea is just monitor something within the body, for instance, one application. To be a bit more specific, in large-scale machine learning and distributed computation or parallel processing. So let's say that we want to minimize this, our friend, which is 1 over n summation of finite number of functions. It could be convex, non-convex, whatever, OK? Then what would happen if n is large? So in this case, individual worker, this should be capital N. But individual worker are responsible to find the gradient. So this is the gradient of this guy is 1. The gradient of the objective function is 1 over n summation of the gradient of individual term. Okay, and then these guys are asked to find the gradients, report back the gradients to the master node. Master node will run one iteration of the whole algorithm, and then send back the new parameter. Then they will do again and again and again. Okay, so in that case, as I mentioned, if n is large, then we may need to go with the stochastic gradient, so it's random sampling. If d is large, d is the dimension of the optimization problem. So the number of variables over which we want to optimize. So if d is large, we might very well go to a sparse solution. So try to somehow promote the sparsity to find the sparser solutions. Or we may need to quantize. So instead of sending a vector of 2 million, we can very well send a vector of, and then having floating point for every entry there, we can go with a bit compressed version of that, and then iterate based on that. We're going to add some noise anyway, but then that noise can be somehow manageable. We will see that when we address communication and computational complexity trade-off. In a multi-agent system, again, we have our friend here. But in this setup, let's say now let's change a little bit the setup, where here, these guys, they do have their own objective functions and some private information that they don't want to share. Okay? So they don't want to share the gradients. So this is a fundamentally different setup than this, because here there is just one master node that takes all the gradients and then run the iteration. But then here, they don't want to share their gradients. What they want to share is just the optimal solution. So they want locally find some optimal solutions, share the optimal solutions with anybody else, with their surroundings. So this can be modeled by a graph, and this graph can be again modeled by a matrix. And in that matrix, we can say that who can communicate to whom. Okay? So we can have some form of private information, and then we can find that, and then we will see actually that we can make it like separable objective functions and separable constraint functions by just reformulating this guy. So there is one global parameter W, but then we can just introduce another variable like zi and then say zi equal to zj. So this is a constraint version of this optimization problem. And if the solution here is feasible, then we can say that the solution here is identical to the solution of the other one. And we will see how we can use consensus algorithms to find these form of solutions. So running an optimization problem or machine learning problem over a network here. And again, we would have a lot of problems in the communication, because if you want to this end here, the main difference with the previous setup is that here you will iterate over the solution of this. So you will ask individual node here to solve this problem with respect to their data. So zi, they find the optimal zi, then they just coordinate those zi's, okay? But then we may need a lot of iterations. So under which condition we can converge to the global solution. So how we can recover the solution of this guy. First question. Second question is how we can address the communication trade-off here. Second question. Another relevant application, which is very similar to the combination of the previous ones, is distributed system, where we have some local information, privacy constraints, and some security challenges here again. So it will change a little bit the optimization problem that we had here, but then abstractly speaking, they would be the same, I would say. Same class of problems. And then the last one is intra-body sensor networks. Again, the same thing happens here. Form of object optimization problem would be the same, where there are some sensors and we need to communicate, send something somewhere. Abstractly speaking, or notation-wise, the problem is the same. Now the constraints could be a bit more strict, for instance. So the communication complexity that we can afford here could be much, much lower. For instance, the rate of the communication could be much, much lower here. The dynamics of the network could be much higher. So in this setup, for instance, we may not need to have a dynamic optimization or stochastic optimization, for instance, but then here we may need to have a dynamic. So we need to track the optimality of the optimal solution. Well, we need to track the optimal solution over the time, because the optimization problem, the landscape of the optimization problem is changing over the time. So here in this scenario, for instance, we might have a time-sensitive decision. So essentially, we do have the same form of problems, but then we might have some more constraints in that problem or not. OK, any question? Cool. So if not, then we can go to the lectures. What are included in different lectures? So what you will see in the next lecture is centralized convex machine learning, where, well, essentially the f function is our friend, the average of finite sum. So that is the machine learning part, just to be honest. So we look at the objective functions in that form mainly, but not necessarily. But then we're gonna summarize and review convex optimization 101, actually, in the first lecture, lecture 2, actually. And in lecture 3, we're going to go a bit more advanced with the stochastic gradients and its variations. And then there are some homeworks here for lecture 1 and lecture 2 as well, for lecture 2 and lecture 3. But then everything there is just centralized. So there is one master node that do everything. But then in lecture 4, we update or modify the objective function to be non-convex, and then see what would happen in that scenario, and what we can say, what are the proper algorithms that we can run. And then lecture 5, we're going to extend the centralized part to go with the distributed part, or actually running something on a network. In lecture 6, we would cover a very prominent algorithm, ADMM, alternative directional multipliers, and we would have a guest lecturer, a former graduate of automatic control here, who has done a lot in convergence analysis and optimization of hyperparameters of ADMM, actually. But then that lecture is not only about ADMM, it's about actually distributed algorithms running over network, in particular ADMM, but then that class of algorithms. Anyway, then that's a bridge to the next lecture, which is communication efficiency. We will see that ADM is just great, But then the problem is that it needs a lot of overheads for the communications. And then actually that brings us to the next lecture, communication efficiency, how we can make it a bit more efficient in terms of communication. Because if we want to run something over the network, then we will see actually that the communication bottleneck could be much, much more serious actually than the computation bottleneck. And then in lecture 8, especially if you use a stochastic gradient type of algorithms. In the next lecture, we're gonna we're gonna look at deep neural network as an example. So that would be somehow a summary of whatever we said in the first 7 lectures. Okay. So we will start with linear regression on one layer neural network without any nonlinearity, and then we add nonlinearity and then some other other layers to make it non-convex. And then what would happen if we want to run that over a data set? So essentially that would be somehow a running example that we will see throughout all these lectures and make it concrete in lecture 8. From that point, you would have 2 weeks, I guess, yeah, 2 or 3 weeks, something like that. From March 6 to 20, so 2 weeks. 2 weeks break, and then you can prepare for the special topics. In a special topic, in lecture 9, we would have large-scale machine learning. I will cover some of those points, but, well, actually I will cover some of everything here, but not all the detail. So one group will be assigned a topic in large-scale machine learning, and they need to prepare for that. So, and the preparation is, we will see in the next slide how to prepare that. But then the next special topic is security in machine learning over networks, and lecture 11 is about online machine learning over networks, where you don't have access to the full data set to run that. So the data set are coming online, and then how you can address the trade-off between exploration and exploitation and all those sort of things. And then a special topic 4 is, which is a lecture 12, is once we want to run machine learning with some partial knowledge. So let's say that we did have an optimization problem. We didn't have any constraint, or we do have some constraint, but there, everything as an input, we did have them. But then here, assume that we have partial knowledge over them. So how we can somehow modify the algorithms to work in that scenario. And then finally, the last one are about application areas. And we conclude this course with some open research problems. Last slide here is about those special topics. So a special topic, we formulated that in the form of a 2-day workshop, so almost full-day workshops on March 20 and 21st of this year, of course. And then between 10 and 17, the room, I'm not sure if it is set or not, but it could be V32. I'm not 100% sure. I will just post that, keep you posted about that. We might have some invited talks. Again, we are not sure about that. But then the whole idea is that apart from those potential invited talks is to give you some exposure of both oral presentations, well, oral presentation, poster presentation, and networking. So every group should come and present 30 minutes of their topic. It doesn't have to be all the members in that group, so some members, just one should be fine. Again, there is a 0-1 loss at the end of the day. And then we would hang the poster. So every group will have both oral presentation and poster presentation. We're going to hang the posters. It doesn't have to be a real poster in A0. It could be just some A3, perhaps, pages printed out. Then you will hang out. Every group will hang out. Group members will will stand together. And then you can have a networking where everybody can walk around and then talk about different topics. So real networking thing. And then it's like integrated. So we have a session of oral presentation, poster, oral, poster presentation. And so the same thing for day 1st and day 2nd. And that's it. And you have until the next lecture to form the groups. Regarding the topics, we do have some potential papers and potential, let's say, references for these special topics. You don't have to have some new things, some new contribution for sure. We do have, well, actually, it's much better if you don't have that and then try to review some breakthrough in the field, some very important references in the field. But then it doesn't have to be just one reference. So it should be a collection of references, so a real research on that specific topic. We have some suggestions on that, but then we are open to some other suggestions. OK. You had a question.
Should we use any specific language or framework for programming assignments?
OK. So the question is about, is it restricted, the computer assignments restricted to any special programming language? No. So whatever you prefer, perhaps Python is the easiest one because you don't need to write down all the codes and load all the data sets. But if you're willing to do that, then you can do that. So there is no restriction on the programming language that you want to use. And then it's not like everybody should do the code. So that's why I said that it's good to have a mix of strengths. So every group can contain potentially one or two that are good with programming, some others that are good with mathematical development, and some others that can help with research. And that can help because it's not like you're going to change the groups over and over. OK, cool. That was it. And some references that I used to create these slides and the next slide you will see. So the first one is a really good tutorial. Let's say book chapter on foundation and trends. It's a bit heavy, but it's really, really good. The next one is one of the references in lecture 8, large-scale machine learning. This is a very good serum review. And then the rest, you will see them more and more. But then this is not the only list. So I would try to provide the list of the references that I use to create every slide at the end of the slide, so you will see them. OK, any question?
For special topics, every group only, for every special topic, only one group can be chosen for that topic, or for some groups, maybe they will choose the same topics.
That's a good question. So the question is about if only one group will be allocated to one topic or more than one. Actually, more than one. It depends on the number of groups, right? So if you have like 5 special topics, and if you have 10 groups, which we would have, then definitely we need to have at least 2 groups per topic. Then it's going to be 30 minutes first group, 30 minutes the other group. And the references that they're using, they can be the same, but they should not cover exactly the same topics, of course. So they should cover somehow different part of that. And then we will manage that.
So there are 2 presentations by each group, one on the lecture day and one on the workshop. Is that the case?
Can you repeat?
Are there 2 presentations by each group, one on the lecture day and one during the exercise, like the workshop?
OK, so the question is about, I'm repeating the question for people over the net. So the question is about are those 2 lectures that we have talked over, so 2 different presentations of 2 different groups, are they in the same day, same workshop, or workshop and lectures? So these lectures are actually, so these lecture from 9 to 13, they are part of the workshops, actually. So it's not a different thing. So and then there is no specific separation in the sense that lecture 9, so first we should cover large-scale machine learning, then we would cover security. So it might be that we will cover security and then larger scale. But for now, we're going to cover special topic 1 and 2 and 3, which is lecture 9, 10, and 11 in the first day, and 12 and 13 in the second day. So 2 groups will present on the first day on larger scale machine learning, back to back, perhaps.
9 to 13 are happening on 20 and 22.
Exactly. So these 9 to 13 will happen on the workshop days.
About homeworks and computer science, what are the expected timing of those? Like, are we going to do 1 per lecture, or what is
interesting question. It's not set for homeworks, definitely. So the question is about homeworks and computer assignments, so just to make it a bit more general, and how much time you do have. It will be specified in individual homeworks, And computer assignments, for some computer assignments, it might be a bit heavy, and you may need to have more than 1 week. But for homework, definitely it's just 1 week. So whenever it's posted, then you will see the deadline, but then usually the deadline is the next lecture. Okay, any other question? Cool, great. Then thanks.